So welcome everyone to this sixth edition of the webinar that we are organizing in our conversation series at UNI Macau since last year. So my name is Serge Stingwish. I'm the head of research at United Nations University Institute in Macau. In this series of seminar, we are discussing the interrelationship between decision makings, AI, and models, as well as their positive and negative impacts on the achievement of sustainable development goals, and the consequence of these impacts in terms of policies. So we are giving the voice to the top researchers around the world in order to hear their thoughts on this very important subject nowadays. So today we have the great pleasure and the great honor to receive Professor Bruce Edmonds for a very important topic on the role of simulation and models in this time of COVID-19 and global challenges. So the title that you propose for your presentation is very intriguing. It's Advanced Simulation Models and Policy, What Could Possibly Go Wrong? So very, very interesting topic. Just to present you briefly, Bruce, so you are the director of the Center for Policy Modeling and professor of social simulation at the Manchester Metropolitan University. So your first degree was in mathematics, and you have done a PhD on the meaning and definition of complexity in the philosophy of science. So you are now working in the field of social simulation and most particularly using agent-based modeling techniques to understand complex social phenomena with policy relevance. So you mentioned also that in your bio that you publish widely, being interested in far too many things for this own good. So it's I guess, it's quite common for lots of academics people, I guess. Yeah. So you can know more about your activities and the Center for Policy Modeling. So at the website, so cfpm.org. So thank you.
Usually you can our website. Usually you can. Our website is just down at the moment, but normally.
I see. Normally it works. So the Professor Bruce Edmonds, the floor is yours now. You have something like 30, 40 minutes for your presentation. And after that, we will have a Q&A session with the audience. So thank you again for your presentation.
Great. Thank you very much for the introduction. Let me just find the slides. Oops. Let's. There we go. Okay. Slides showing all right?
Yeah, perfectly.
Okay. So, there we go. First part, some motivation and discussion, and then the second half will be an example simulation and how it might work. So the key questions here: how does one manage a system or situation that is too complex to predict, which is a difficulty we face increasingly? How can complex simulations help in these situations, and what should be avoided? I won't give a complete answer to that, but I'll start discussing that. So you start with the cautionary tale. In 1992, they had to put a moratorium on all cod fishing off Newfoundland, and lots of people lost their jobs. This is despite the fact that scientists and fisheries departments through much of the 80s estimated a continual great rate of growth in the catch. And there was a subsequent investigation into this, and it said scientists lulled by false data signals and overconfident of the validity of their predictions failed to recognize the high risk involved. So they had unreliable data series. But they also had another aspect of what went wrong, was that their analytical models were very simplistic, very hypothetical, very, it only sort of dealt with a few sort of variables changing. Finlayson also concluded that the social dynamics between the scientists and the fisheries management was at play. Scientists seem to have adapted to the wishes and the worldview of the managers gaining confidence in their approach from the apparent point of science. So here's an example where modeling was counterproductive. It helped create the crisis by giving the managers confidence that the fish stocks were continuing to improve and that current levels of fishing could continue. So here we're going to look at the whole issue of using complex analytical models with policy. That's what the whole talk is really about. So I'm now going to look at a number of other areas and try and just talk about motivate by analogy. And the first one's a little fine, so a little odd. So looking at how people trying to design robots in the 70s and the 80s. Now, the purpose of this is a robot has to deal with a really complex environment, ones that are outside a factory and stuff like that, ones that are trying to wander around in real life. And in the 70s, 80s, what they tried to do is get these little robots to build a map of the situation around them, use this map, this model, to plan its best action, try and do the action and check it was doing okay. Now, this approach did not work, basically. First of all, it was far too slow to react to its world. And to make usable predictions, it had to make too many dodgy assumptions. In 1991, a person called Rodney Brooks tried a different approach. He got little robots to sense the world in rich, fast ways. So there was an emphasis on sensing, react to it quickly, and have a hierarchy of decentralized decision-making. So in this little robot you see in the picture, even the legs have sensors and decision-making down at the end, and then higher levels of decision-making further up. And the whole motto of this is do not try and predict the world, but react to it quickly. This worked much better, producing robots that actually could move around and deal with some of the complexity of the world around it. And obviously, I'm going to suggest that maybe in terms of trying to deal with our complex world, we should take on some of these lessons. Let's look at weather forecasting. For many centuries, weather forecasting involved in taking measurements at a few places and trying to predict what would happen based on very simple models, based on averages. But understanding of the weather improved as soon as we had very detailed simulations fed by a rich and comprehensive sensing of the systems. Lots and lots of sensors sensing what the state is, satellite photographs, etc. And even then, with all this technology, they recognize there's more than one possibility concerning the outcome. So what they do is that they run their model lots of times with slightly randomized conditions starting from what's being observed currently, and then look at the whole collection of predictions and decide what can be forecast reliably. And particularly if this indicates a risk of severe weather, they issue a warning. So you can take mitigating measures for this. Let's look at radiation levels. The human body is a very complex system. It's been long known that there are too much radiation cause severe illness. In the 30s or 40s, it was assumed from the simple models that there was a safe level of radiation. That is, when the radiation level came down to a certain level, it was okay below that. However, later, a more accurate model was that maybe any level of radiation carries more risk of cancer, including naturally occurring levels. So although a risk in radiation might not seem to affect more people, it in fact invisibly resulted in large numbers of extra cancers spread over the wide populations. This is an area, I must say, of still active debate in the community. Now, we are faced with a whole lot of systems that we need to deal with, and they are doubly complex because they're a combination of social systems, us, and ecological systems. And the management of that interface is critical to both our survival and the healthy survival of a lot of life on Earth. So for example, fisheries, deforestation, species extinctions, and yet we still use basically the 1970s approach of predict and a plan, as if we can plan optimal policies, for example, in the optimal land use or optimal fishing levels. To try and manage that. All of these approaches are based on fairly simple models. And unfortunately, simple models don't get things right. But worse than that, they don't even get things roughly right. It's not the fact that you do a simple model and it gets roughly right, and you add in some detail and it gets a bit better. Typically what happens is there's a minimum amount of detail you need in the model to even get things roughly right. Simpler models like this are not more general. Okay. They can also be very deceptive in the fact, because they don't show all the complicated ways things can go wrong. They are often far from equilibrium, which is what is assumed in lots of ecological and economic models, and far from the average behavior. So the average behavior is often not a very good guide to what is going to happen. And they often have very strong assumptions in them. And they give false confidence to those who are basing policy upon them. So in a sense, they can be far worse than having no models at all, as in the Newfoundland cod fisheries example. Complex simulation models, they're like weather forecasting models. These track the interactions of millions of entities. Okay, they're not just tracking bits of air and cloud and rain, but they also are used in many other areas like logistics, ecological management, epidemiology, urban planning, social media analysis. All of these sort of areas are now used, these complex simulation models. The big advantage of them is they can be indefinitely checked. Once you've got a model, you can experiment it with, you can look at all the detail, you can check it, you can run lots of experiments, you can compare it with the data and lots of alternative simulation models. So it gives you a big advantage to understanding very complex situations. There is, if you're interested in the whole world of complex simulation model, there's a good accessible UK government report which surveys them and introduces the whole area in a nice way, accessible to policymakers. If you just Google the name Computational Modeling Technological Futures, you will find this report. Of course, complex simulation model has come very much to the fore during the COVID pandemic model. We've started to hear about complex simulation modeling. Famously, the Neil Ferguson team in Imperial College in London was one of the factors that influenced the government to change policy in the UK. Unfortunately, this is a very easy target for those who disagree with the simulation results. Because these models always involve assumptions, but you can always say, but they didn't do this or they assumed this. And also there's an expectation that these models are for prediction, that they were for predicting what is likely to happen. Such modeling is often opaque. You can't really understand unless you're an expert what is happening into the modeling. They're often detached from the policy process and from stakeholders. And it's often seen as a purely technocratic exercise. The modelers go away, do some modeling, come back and tell you the results. So policymakers obviously have an uneasy relationship marked with misunderstanding, certainly in the UK, and there they were relatively well integrated in the policy process, but still there were lots of tensions and misunderstandings there between them. So the downsides of complex models are that they're very difficult to understand, even by the modelers themselves. Okay, they're generally, I would claim, not suitable for predicting what is likely to happen in the future, even though that is what is desired by policymakers. So the whole idea of trying out different policies in a model and finding out which policy is best doesn't work with complex situations. The whole methodology for using these complex models to help with policy is only just emerging. It's starting to develop. There's this difficult policy world analyst relationship. The policymakers are stuck in a bind. If the models are saying something different from their intuitions, what do they trust? Do they trust these technical geeks who are saying something different to what they understand, or do they trust their intuition? How can they trust these technical geeks? Can they trust these really complicated models that they can't check themselves? That's a really difficult relationship. Often these models assume assumptions about values. They go further than just technical simulation. They assume what is desirable or what is being aimed at in terms of the outcome. For example, the COVID model is often assumed that we're trying to minimize the number of deaths. Okay, there's no balance in these models between that, for example, and the economy or people suffering or anything else. And the effect of models can be to limit input. Well, as soon as you've got a model, people concentrate on the inputs and outputs of that model, and other aspects, other viewpoints, other approaches, other streams of evidence can be ignored. So in the Newfoundland cod collapse example, the fishermen were actually telling the authorities that they were worried about the fish uptake and the fish stock. But the modelers and the managers thought things were okay because their models predicted otherwise. So they ignored the input of the fishermen in that case. So the models can have the effect of limiting what is considered, which is a negative outcome. Here I'm suggesting a different approach. For complex systems where it is not possible to predict what is likely to happen, we should give up on predicting that or trying to optimize policies. We should make simulation models that include more of the observed complication and complex interactions and incorporate a wider range of inputs from stakeholders and people that are involved. We should then run these models lots of times with various scenarios to discover some of the ways in which things can go surprisingly wrong or surprisingly right. Okay, so this is not a probabilistic approach. We're not trying to find out what is probably going to happen, but a possibilistic approach. We are trying to find out what could possibly happen. Okay, so that's a weaker task from the more easily reachable task for simulation modelers, and I think more practical. How does this advantage the policymakers? Well, when you know how things could go wrong, you can place either measures, contingency measures, in case that eventuality happens, or ways of sensing, measuring the environment so that you know when it might be happening. So in the example of COVID, there are now lots of centers that are measuring when new variants appear and when they start to come out. For example, doing DNA analysis on wastewater. And those early warning indicators give policymakers more warning about what would happen, and the policymakers can react sooner, quicker. Like those little robots, they can react quicker to the real world and change their policy to adapt to it. So I'm going to give you an example model of my own in terms of fishing in a complex ecosystem. Now, the kind of complex modeling that I do is called agent-based modeling or individual-based modeling. This is where every single individual is separately represented in the computer. Each can have its own properties or behaviors. And the interaction between these is also explicitly modeled. The simulation is then run to see what unfolds, sometimes in unexpected ways. The way I sometimes explain it, it's like programming a whole room full of robots. Each robot has a different program, and then you stand back and you press the go button, and then you watch these robots run around and bump into each other and interact and see what occurs. This is the equivalent of what we're doing in the simulation. You then analyze and visualize the outcomes and try and understand how they came about by tracing back through the simulation. Okay. So the model is a fisheries model. So it's got plants, it's got fish, it's got space, it's got different environments, patches of different environments, energy from the sun, and each of the individuals here have their own gene to determine its behavior, its own energy, its own position, and they all eat each other and survived. So here we go. How do we work out? Well, we literally evolve a complex ecology. So we run the simulation over a long number of time. until there's a first successful plant, and then the plants spread, and there's more species of plants as they mutate and evolve. And then we, in this case, inject some fish into the simulation once the plants have got established, and then the fish evolve. They start by eating the plants, and then carnivores that eat other fish evolve, etc., etc. After a while, we got a balance of all the trophic layers. Then we freeze this simulation at that point and use that as the starting point for a series of risk analysis simulations. So we freeze the simulation at that point, and then we run it forward with different fishing policies to see what might happen. Okay, so I've probably explained some of this already. Yes, I've already explained that. So classically, in fishing terms, people assume that there is a level of fishing that is sustainable for that ecosystem, so that you can fish up to a certain point, and that's okay. If you fish too much, of course, you have a dangerous impact, but it is safe to fish up to that level. That is rather like the radiation example, where people assume that there is a safe level of fishing that doesn't impact on the ecology. Now, that's true when you use very simple models, but in this complex model, we get a slightly different picture. So if you look at the orange line, this is different levels of taking fish out, how much fishes are extracted per time unit. And you can see there's a maximum here. This would be the optimal fishing level in this particular model. But when you look at over lots of runs, how many times do all the fish go extinct out of 20 runs? You can see by this level, 10% of the time at this maximum level causes all the fish to go extinct. So it may be an optimal in some sense, but it's not a safe optimum. The safe optimum is maybe almost half that. And at higher levels, of course, in all the runs, the simulation, all the fish, the species go extinct. So the advantage of having a model is then you can now go and look at it. So here's 20 runs of the same simulation, starting at this same frozen ecology, and then running it forward with different levels of fishing. So here we're running it at a certain catch level, a low catch level, and you can see in the model, naturally, the levels of numbers of fish varies. So for example, in this run, you can see it's all over the place. And in this run, it stays up there, but then it goes down a bit. So each time you run it, starting from the same complex ecology, you get maybe very different, almost chaotic outcomes. If we're catching a few more fish, what happens? Well, sometimes they're all right, but in a few cases, we kill all the fish off. What seems to be happening? In all cases, you get a big variation of fish levels. And in some cases, it tends temporarily to go down to a low level. And if you remove fish at that time, that's when the whole ecology is vulnerable. Of course, if you have a higher level of fishing, then some of these cases, they all go extinct immediately, and some cases later. There are still lots of cases that the fish don't go extinct, but that depends on the particular connection and food web that was existing. So if we look at the different numbers of catch levels of fish and the average number of fish at the end of the simulation, it sort of goes down, unsurprisingly, because we're taking fish out. So there's going to be less fish left, and then a sudden decrease to the fishery collapse, classical fishery collapse. But when we look at the number of species levels, it's relatively flat, and then suddenly all the fish go extinct in all of these runs. If we zoom in to the low levels of fish catching, we see that even when we do low, very, very low levels of catching fish, 5, on average, some of the species go extinct. Now, here is the difference between the simplistic models and the complex model. In a mature, evolved ecosystem, there are always some species on the edge that are only just surviving, only just competing with all the other species. Okay? And as soon as you take energy out of the system by catching fish, you're going to kill off those marginal species. So there is no, according to this model, there is no safe level of fishing, but there are different levels of fishing impact. Let's look at one more example, how you catch fish. So here we're comparing two different methods of catching fish. One is you go to a patch, you fish there until you've caught at the same level until you caught all the fish you can. And then when there's no fish there, you move to a different patch and then you catch all the fish there. Compared to a method where you catch fish sort of uniformly over the whole area. So when we have a very low level of fish catch over time, there's not much difference. Slightly higher catch level of fish, you can see a little bit of difference. But above a certain amount, suddenly you can see that the by patches method has a much bigger impact upon the number of species left than doing it uniformly. Here is another way that things could go wrong that we didn't expect just from a simple model. So almost finished now. So conclusions from the example. We don't know how realistic the evolved complex ecology is in this simulation because it's an artificial ecology, although complex. We do not know whether it matches any particular ecology, but so it doesn't predict what is likely to happen, but it does show how things might go wrong in ways that simpler models cannot. Using visualizations, these kinds of outcomes can be then consulted upon, stakeholders can be involved, policymakers, there can be a discussion about those particular approaches. And then maybe mitigation plans agreed or targeted monitoring implemented, ways of measuring the fish or whatever system you're looking at. So policy reaction can be reactive as policy. Overall conclusions, complex systems cannot be relied upon to behave in regular ways. Often averages, equilibrium are not very informative. Future levels can often not be predicted. Some systems it can, but there are some systems, especially ecology and society, where it can't. Simpler models may well make unreliable assumptions and not be representative. Complex models can be part of a risk analysis. They are difficult to use because they are difficult to understand, and there are difficulties in the policy analyst relationship. But identifying some of the ways in which things can go wrong as a sort of way of improving resilience, implementing measures to watch these so that policymakers can react as quickly as possible is a positive and possible way forward. In a way, what we're trying to provide the policymakers with is the ability to drive policy, to look out of the front windscreen of their car and see what might go wrong and be able to react in a timely fashion. Some of this work was done with my PhD student Leah as part of the SAF21 project, a European funded project, which is social aspects of fisheries for the 21st centuries, which is why the model is about fish. If you want to read the full paper, once our server is back up and running in a couple of weeks, you can go to this link here. And there we discuss in lots of details, lots of different ways that modeling can go wrong in the policy context. Okay, and this is a short link for that introduction to complex simulation if you're interested. And that is all. I guess maybe Sergio would be able to share the slides, hopefully, since it's not available on the...
Yeah, sure. And we will share the slides on our website. Thank you very much for your very insightful talk. So I guess we have questions in the audience.
There, I was less than a minute per slide.
You have been very fast, yeah. I have a first question, maybe to warm up a little bit the audience. So you mentioned that at one point that simulation was a kind of technocratic exercise, and I tend to agree with that because most of the time this is a discussion between experts. So our decisions that are taken by policy makers with these models can be accepted by the citizen, and I'm thinking, because I'm working in the UN system, I also think this is important to hear the voices of the people from the global south, people that are also coming from marginalized populations. So how we can add this voice in this kind of simulation model.
It's a difficult question. I've only got partial answer to that. I think by consulting with stakeholders about a number of things, first of all, you can consult them about the values. What are important to them in this situation? What should be the goals of the simulation exercise? That's very important, because often the goals are assumed by the policymakers because they have their own concerns. But secondly, and this is an area that's only just sort of emerging, you can ask stakeholders about some of the information about how they behave, what sort of strategies they use for different circumstances. So they might tell you, I try and guess, look at the long-range weather forecast and decide what to plant or something like that. Or I base it on last year unless it's a disaster, something like that. And these sort of strategies, agent-based modeling, it is possible to include those sort of strategies in the programming of the agent-based models. Ideally, you'd also want things like surveys to find out when and where these strategies were deployed. But if we're looking at a sort of risk analysis, we want to see, with different mixes of strategies amongst the people, what could go wrong, and find out some of the ways of the interaction between the ecosystem and the people, the feedback loops, that you couldn't predict. So lots of farming decisions, for example, or fishing decisions have had unforeseen consequences. The Netherlands is battling at the moment with too much nitrogen happening around. Nitrogen was a good thing. It grows more crops, but it seems to be more complex than that. So there are a number of ways. And then, of course, once you have the results, try and involve people in looking at these results and commenting upon them and seeing what they think is realistic and what isn't, and having maybe citizens' parliaments or discussions about those, involving them to try and understand why these models are suggesting these things, and also critiquing the models, trying to make them more open to critique. So trying to bring in more people as well as the policymakers, I think. This is not easy. There are people in my field who do this much more than me, but it is possible, and it does help with the whole process of trying to influence and inform policy in these situations. I don't know if George has anything to add.
I actually think that you mentioned a very important role for models here, right? Because I would immediately agree that predicting using models is somewhat of a ridiculous exercise. But making the model together with the stakeholders, everybody is modeling, although most of them don't realize it, but they see the world in a simplified way. It's just, if I do this, then that will happen. And building a model together at least exposes you to the fallacies of your own thinking.
Yeah, it can do that. It can very much surprise you. You can also fool yourself with models, though. When you get really involved with a model, you start to believe your model. The whole world starts to look like your model. I have the effect where the whole world looks like my model for about 3 days after I finished it. Everything looks like my model. And this is a very strong effect because you're really involved, you're tweaking, you're interacting with your model, that it affects your perception. So you do really need to step back and get in other people's critique. to try and shake yourself a little bit out of that complacency and worldview. I don't think it's bad, but as long as you
and I guess for some
are aware of it
for
and
some,
have other ways to help.
For some stakeholders, also some concept of the complex system theory might be difficult to understand. I try to think, for example, about the exponential growth. It's very difficult for stakeholders or for citizens to understand that. So if you have this kind of simulation models, you can experiment directly this kind of concept, and it's much more easy, I guess, after that to understand the issues around.
Yeah, I think we need a range of techniques, sort of maybe little, very simple, simplistic simulations to play with, that people can play with and can experience, for example, exponential growth, and trying to keep a little certain level at a certain level where exponential growth is happening and how difficult that is, or something like that. But also the use of visualizations. Often I don't think trying to present a whole complex model is feasible. It's just too much. But if you design a visualization of the underlying data using your understanding of what might go wrong to sort of highlight this, people understand visualizations of data a lot better, a lot more transparent. And these sort of ways need to be developed to help the communication process.
Although it's also very easy to lie with graphs.
Oh, yes. Yeah.
We have.
It's very easy to convince people with a nice animation. Yes, you've got a beautiful little animation, and it looks real, it feels real. Yeah, yeah. Hello, you got a question?
We have one question from Lawrence Vin. Sorry about maybe the pronunciation of your name.
Oh, no, that's quite good. Thank you. Thank you. Very nice presentation. My name is Laurens Veen. I'm a research software engineer at the Netherlands eScience Center, which makes me kind of half software developer, half computational scientist. I've actually worked in the past in ecology with metapopulation models. So I'm somewhat familiar with the topic. What I'm wondering is, your conclusion is that modeling these complex systems is too difficult and that we cannot do it at a probabilistic level, but that we can at least try to simulate them and model what is possible. On the other hand, you also mentioned weather forecasting, which are also complex systems. And well, especially in recent years, the weather forecasts have actually got quite good. I can look at the weather forecast and for several days.
Absolutely. It may be in 100, 200 years time, we can predict some of these complex systems, but we shouldn't claim that before it's very well identified. And also the weather, although it is a complex system, is relatively simple compared to these systems that we're talking about. You know, we understand the underlying physics, for example. We know how the atoms move. It's relatively easy to measure in bulk what's happening with social systems or ecological systems or fish under the sea. We really don't know how many fish. They rely on how much is caught by the fishermen to guess how much fish there are underneath. I mean, it's really very, very poor data. And so I fully agree. I mean, you've got to judge it for that situation. So yes, maybe in hundreds of years' time, we'll be able to say we can sort of forecast it in a sort of weather forecasty way, sometimes being wrong, but often being right, maybe. But we've got to be honest about the current situation for a lot of these situations.
Yes, I do agree with that. I also recognize very much what you were talking about, just that it's very easy to convince yourself of the correctness of your model and that it produces all sorts of things and that you understand what's going on until you discover there's a bug in the software and realize that actually the results were nonsense. But what it really means is something else.
Absolutely. I have the experience of slowly debugging my model and the results becoming less and less interesting as I find each bug until it's a really boring result. Sorry, I interrupted you. You were saying finish.
It seems that there's also an effect that as in particular for ecology, that as humans affect the landscape and the ecosystems more and more, the ecosystems tend to become simpler. And we cut down a tropical forest and replace it with a plantation. which is ecologically a much simpler system. So maybe at some point our models will become advanced enough and our systems will become simple enough that we may be able to actually simulate them.
Yes.
Assuming we have enough data.
Yes, that's right. That's absolutely true. As humans, we construct a simple world around us that is much easier to deal with than the natural world, so to speak. We make houses as a rectilinear, we have people and we have roles, we have times. You know, we simplify things by imposing that upon reality as a way of dealing with the world. Instead of predicting complex nature, we simplify it, and you're absolutely right. And that is a big impact of what happens. And then maybe that's going to be more simplified, more predictable, what happens in the fields, because they plant the same thing over a whole field, you know. Yeah, I don't know.
Farmers collect.
Sorry, two more questions.
Yeah, we have two more
yes.
questions. Yeah. Sorry. Hubert, you want
We're
to
always
start?
simulation models are always short of data. We're data starved. You think we're in a big data era, but it's never right. It's never the right kind of data.
Yeah, so hello, I'm Hubert from Wageningen, working with George on agent-based models. But also I have a background in risk modeling and management in financial institutions. And I really like your emphasis on using these kind of models as kind of bringing risk awareness to stakeholders. I worry, though, that if you give this to the wrong people, that they will just see a bunch of curves, say, oh, well, let's take the average, let's take the standard deviation, assume that the simulated standard deviation around a certain outcome is correct, and then we can price that in, or we can. Yeah. So I think I think the kind of emphasis on sensing, direct sensing of your environment, and also maybe taking small steps towards your goal and evaluate, I think that's even more critical.
Yeah, you're absolutely right. I mean, for example, in the insurance industry, they assumed that sort of basically sort of normal distributions of risks for many decades, until they realized that these were leptokurtic, that, you know, there were that extreme events were much more likely than their models predicted. And that was a sort of averaging assumption of exactly the kind you're talking about. And it took quite some big shocks to make them to realize otherwise. And that does happen. I mean, the Bank of England does model-based risk assessment of banks, where it tries to stress test them, but they're very simplistic models. Are they giving false security? They can't model all the interconnections between banks, so how a difficulty contagion spread, like in the last financial crisis. They sort of try a bit, but, you know, they don't really get those risks. So it needs to be emphasized that this approach can reveal some risks, but they never reveal all risks. You then got to add intuitive-based, just expert-based assessment of risks as well. It mustn't just be model-based risks. Yeah, absolutely.
Thanks.
Natalie?
Natalie, you want to ask the next question?
Yeah, thanks very much. I was wondering, one thing I really liked about your presentation was how you kind of went through the results and explained this model. And I felt like the results were, you know, even if the model itself was not simple, the results were, you know, they very much made sense. And one thing that I sometimes struggle with is kind of how to design my model in such a way that both takes into account maybe the complexity of the system, but also gets me what I need in order to answer specific questions. So for example, I work on a project looking at the Dutch food system. And, you know, as part of that, there will be, you know, maybe specific scenarios they're interested in exploring. And so I was wondering if you could talk a little bit about kind of the process behind developing your model, both keeping like looking to the complexity of the system, but also thinking about how to get results from that model that will be, you know, explainable in, you know, maybe a policy context.
Yeah. Absolutely. So about half of the programming time is just spent making the model, but then the whole other half is spent programming in just playing with different visualizations, different analysis, different output of the simulation to try and find out some understanding of what's happening. And it's, one can jump to conclusions about what is happening in the simulation, but that is very dangerous. So you have to spend a lot of time just visualizing it in different ways, different outputs, different things. My models tend to have page after page of graphs and simulations and visualizations down there, all of the same model, trying to get some understanding. And here we're using the classic scientific method. You're hypothesizing about your own model. You're trying to understand why it's giving out results. You then do an experiment to test your hypothesis and see whether it was correct. So there's a sort of informal playing with stage where you're just visualizing it. You're trying to do induction, measuring it and visualizing it as many ways as possible. And then you have a hypothesis, and then you should, if you're doing it more rigorously, do simulation experiments to test your hypothesis. This is just hypotheses about your model. It's not about the world. It's just making sure you understand your model. And based upon those, so there was a lot of work. I mean, I just invented this simulation initially just for fun. Okay. And I wanted everything to evolve together and everything to eat each other. And I just wanted it all in there to have a good play. And then, it took me ages to understand what's happening in that model and it's still quite complex. So to try and tease out bits that were understandable were the result of a lot of work. It wasn't just instantly obvious what's in. So there's still lots in that model that I don't understand. But yes, we need to put a lot of emphasis, as you're sort of indicating, on that side of modeling, coming out, analyzing the results, making it visible, making the assumptions visible as well to people, so people understand how it's working, maybe little simulations to play with, maybe more advanced visualizations of the underlying data without the model at all, different ways of communicating and understanding that. Yeah, I think that's absolutely, we need a lot more work in that area.
Thanks very much.
Yeah. Sometimes what I do is I follow a single agent in the simulation, like a single fish, and then generate textual outcome of what's happening to it. And then you can go to a fisherman or something and say, is this plausible? Okay, it's a bit silly with a fish, but it's more sensible when you have other social simulations. What happens? Do they then vote for this party, then don't vote for this party, then moved country? What happened? And you get a sort of pseudo narrative of a single individual in the model, and get an idea of whether that's plausible at the micro level. That's another area we could generate sort of stories and narratives that people might be able to critique and understand. Anyway, sorry. Yeah.
Do we have more questions for Bruce?
Oh, there's one in chat. Okay, Adam. Proof of hypotheses take a long time and data preparation takes longer. Yes, this is completely true. And often the amount of time to do good simulation modeling is hugely underestimated by policymakers and the modelers themselves sometimes. So it's not just the programming and making the model to start with that's the time. It's then the engagement and the trying to understand the model and the data preparation. Yes, I would love 20 people assisting me who are just going out and looking for data, preparing it for me in a nice format. This is heaven, but it never happens that way. You're always left trying to understand data yourself. I don't know whether that rings true with some of these other modelers, but grappling with the data, and this is all a long time, yes. And sometimes you don't get to some good understanding. You just get to a negative outcome. You haven't generating in new understanding or something that you think is worthwhile, and you've just got to be honest about that. I think it's a bit difficult in a policy-oriented situation where they want answers. If you just give them negative, it's a bit complex, because that's what they sort of expect of academics. Academics always tell them it's more complex, and that's very frustrating. There's quite an interesting there was an analysis of how policy analysts technical analysts and policy people interacted during the foot and mouth outbreak in the UK about 10, 12 years ago. And one thing that happened is that when the results from the analysts were given to the civil servants and it went up the tree to higher and higher ministers, the caveats were always cut off. So just the conclusions without the caveats went up. So as a result, the scientists concluded even less the next time, okay, because they were frightened that it was just going to go out without the caveats. So they actually finally, at the end of the epidemic, they came to an agreement whereby the caveats wouldn't be cut off as it went up to the minister. And then the scientists were willing to conclude something. Otherwise, they just didn't want to at all. So this sort of agreement, these sort of protocols between the policy world and the analytical world, ways of working, needs a lot more development,
I have a question that for sure is quite difficult to answer. It's that what would be the role of models and simulation in the UN system to achieve the Sustainable Development Goals? Do you have any ideas about that?
Well, I think the UN could play a role in sort of trying to connect systems and seeing how systems can go wrong together, because often particular governments and agencies are looking at little bits of interconnected problems. They're not looking at how, for example, changes in society and changes in the ecology might reinforce each other in bad ways, or how changes in the logistics structure in the world could affect ecological systems. So ways of actually connecting these together, which goes beyond nations and beyond particular systems, I think that would be really helpful, trying to foresee some of the ways things might go wrong in the future. I think that would be a valuable thing for them to do.
Definitely agree with that. Yeah, most of the people, they are just working in silo. They work on some specific SDG, and they don't see the interrelationship between the different systems. Yeah, it's quite important to do that. Cara, you have a question? I see you raise your hand.
Oh, no, I was just clap reaction. So
okay.
Yep. Thanks. Sorry.
Well, that's good. That's good. Yes, which of course gives me a wonderful excuse to add even more detail into my models, which I like doing. But yes, these sort of cascades of difficulties, I think if we could get some handle on at least some of those, we won't get all of them, but some of the possible dangers and difficulties, especially with climate change and especially with growing impact of humanity on the world in the ecosystems, it would, even if we just help a little bit, that would be well worth it. Of course, there are lots of politics involved, but as well, so it's not straightforward, but that's what United Nations institutes are for, isn't it?
Sure. So any more questions in the audience?
I have a question.
Okay, Vittorio, can you?
Thank you. Thanks for the wonderful presentation, Bruce. I'm Vittorio Nespeka from University of Amsterdam. That was very intriguing to see some kind of a risk assessment and trying to take that risk assessment several times along the way, right? We manage and adapt. And we've seen in the COVID-19 crisis that a lot of models were used. I wonder if and how, if you have any ideas of how, when such an unexpected crisis, or maybe it could have been expected, but we weren't prepared anyways. With such an unexpected crisis, you could develop models that you can make such risk assessments on the way in a more agile manner, right? We don't have a lot of time. We are under pressure to make decisions. So there's not a lot of time to look for the data if it's even available. So can we reuse some of the things that were available before, and to what extent, and can it be done in an agile way? That's my question.
Yeah, I think we can do better. I mean, it's not there's a wonderful issue of the 2017 Time magazine where the front cover says the next pandemic, and there are really good articles in it which sort of anticipate huge numbers of issues, Trump, vaccines, everything in that issue. So it wasn't exactly, some people were trying to warn us, okay, who just didn't listen enough. But for example, if you take the Neil Ferguson model of the epidemic was based upon his Nature paper on flu epidemics about 10 years ago, where he just produced a whole lot of C code and wrote this paper, but he wasn't forced to publish the code on a public archive, for example. So nobody was looking at that code, comparing it, improving it, discussing it in the 10 years. And he suddenly was called in, he had to hack his code to get some answers for this new epidemic. Now, if we can get to a more mature way of working, that people's code and models are out there, they're public, that people can compare and critique the important ones, that we can develop them not instantly, but over a period of time, critiquing and honing them, even if it's a different disease, we'll be in a much better position to write the model for the next epidemic. So we have to go beyond this where individual scientists are just doing their own stuff, where we're comparing and collaborating and checking each other's work and improving on each other's work. It has to become a much more social aspect, both in terms of consultation, but also in how we work in these situations. In a sense, everyone would needs to take a little bit of responsibility for the modeling. Providing input, scoping its values, etc., like that. So we, over this period of time, and we have to iterate our models over a longer period of time collaboratively. Absolutely, yeah. Hubert Fontaine says you have to assume that critique is in good faith. That's always a starting point. You have to assume it's in critique. You have to take any critique and consider it. You can't just take critiques on face value. There's a whole lot of politics that could be behind the critique, which might be positive or negative politics. For example, it might be voices that haven't been heard in the situation up to that point, positive politics, or it might just be vested interests coming in the critique. So yes, there has to be a whole sort of political system that's supporting the modeling, not just a technocratic exercise. There has to be experts in that interface, in the politics, dealing with critique, being open to critique so everyone has a voice, but somehow distilling that so it's useful critique for the modeling. That's not a technocratic exercise, that's a political exercise. We have to learn how to do that process. It's an extension of democracy in a way, how to make our modeling more democratically accessible and accountable.
Yeah, the accountability and transparency are very important, I guess, for models, Do we have more questions in the audience? Maybe we can stop the discussion now. So thank you again, Bruce, for sharing your thought on this very insightful presentation. So thank you, everyone. Oh, we have a last minute question. Zenit, you want to?
Oh, no, it's clapping.
Clapping, yeah. So thank you for being part of this seminar. We will organize more webinars in the future on the same topic. So so please have a look to our website, so macao.unu.edu, or on Twitter handle also at UNU Macao, so you can find more information about our institute also.